Alright students, in this video we're going to talk about some more examples of be able to draw the resonance structures. So to begin with, let me take an example of NO3 1 minus, and you may recall this is called a nitrate ion. Okay, so let's draw the Lewis-Dot structure of nitrate ion first and then see if we can have multiple resonance structures on this one. So first step is going to be the total valence electrons. We have 5 in the nitrogen. We got 3 oxygens, each oxygen having 6 valence electrons, and then there is a 1 minus charge, means I'm going to have to add one more electron in there. So that adds up to a total of 24 electrons. The next step is finding the central atom, and in this case, nitrogen being the least in number and also the less electronegative would be your central atom. So I'll go ahead and put down the nitrogen at the center and put the oxygens as far away from one another. Okay, in the subsequent step, you want to place one bond or an electron pair between the central and the surrounding atom. So when I'm placing one bond between the central and the surrounding atom, I actually used 6 electrons. Okay, so that leaves you with 18 more electrons to go. So what I can do, I can go ahead and fulfill the octets of the surrounding atoms, like that's the usual next step. And when I do so, I'm going to have to place 6 electrons on each of the oxygens as 3 lone pairs. And that uses up the remaining 18 electrons. So for right now, you want to make sure you have used all the electrons, and that's what we had, make sure that we used all the electrons. And before you finalize this structure, we have to make sure the octets are completed, because if the octet is not completed, then it's a bad resonance structure. And in this case, each oxygen seems to have 8 electrons, so all of those oxygens are fine and they have 8 electrons. But when you look at the nitrogen's right now having only 6 electrons, because it's got 3 bonds around, means it has only 3 electrons, 6 electrons rather. Then what can be done to make sure the nitrogen also have the octet completed? And one of the things you can do, obviously, here to use one of the lone pairs from the oxygen. And let's say for right now I use the lone pair from the right oxygen to create the double bond, because I can't really just put the lone pair from the oxygen onto the nitrogen, because that will make this oxygen electron deficient. So to make sure both oxygen and the nitrogen has the oxygen completed, I'm going to have to put a double bond between those two. And right now I used this the lone pair on the right oxygen to create the double bond. So when I did that, the structure looks like this. We got a double bond on the nitrogen and one of the oxygen. It's 2 lone pairs there, and then we have 3 lone pairs on the other 2 oxygens. Okay, so now everyone is happy in terms of the octet. So now the next thing you want to do is make sure you can figure out what the formal charge is going to be on each of those. So the formal charge, let's look at this oxygen. The formal charge on that oxygen is going to be, I have 6 valence electrons minus how many lone pair electrons? I got 3 lone pairs. That brings in 6 electrons total. And then plus there is 1 bond, so it's going to be 2 divided by 2. So that gives you a -1. If you have a hard time calculating the formal charge, I had another video linked to the end of this video. Make sure to watch that one, and that explains how you calculate the formal charges in details. So this oxygen has a formal charge of -1 right now. Now the oxygen on the top is in very similar situation to the oxygen that's on the left. So that means I'm going to have a -1 formal charge on the one on the top, okay? And then the one on the right, I can just go and calculate the formal charge, the one on the right oxygen. That's going to be 6 minus, I got 2 lone pairs, that brings in 4 electrons, and then plus I have a double bond brings in 4 electrons, so 4 divided by 2, that gives you a 0. So remember, whenever oxygen have 2 lone pairs and a double bond, or 2 bonds total, it has a formal charge of 0. So this is a 0. And then I can go ahead and calculate the nitrogen. So let's do that on the top there. So the formal charge on this nitrogen, I got 5 valence electrons minus. Okay, so then I got no lone pair on the nitrogen, so just go ahead and write down 0 there. Plus I have 4 bonds around nitrogen, 1 double bond and 2 single bonds. So 4 bonds going to bring in 8 electrons total, so 8 divided by 2, and that gives you a positive 1 formal charge. Okay, so even though you have multiple atoms with the formal charges, your overall charge in the molecule still comes out to be -1, because you got 2 oxygens with -1 each, that brings a total of 2 minus, and then you got this nitrogen with +1, so that gives you an overall charge of -1. And if you go back, the nitrate does actually have an overall charge of -1. So remember, you must have the same, the sum of all the formal charges must equal to the overall charge of the molecule. Now here's the next question for you guys. The question is, okay, why did we create a double bond between the nitrogen and the right oxygen? Why that oxygen is so special and we did not create the double bond between the top oxygen and or even the left oxygen? And the answer is, well, the right oxygen is not very special. You could create the double bond between the left oxygen or even from the top oxygen. So what I can do, if I use the lone pair from the left oxygen to create the double bond, then your resonance will look like this. Okay, so this is going to be your new resonance structure in that case. And the only difference between this resonance structure and the other one we have actually drawn is just the placement of the double bond. Other than that, everything else is the same. I'm still going to have the oxygens with a single bond, a negative charge, and the nitrogen is going to have a positive charge. The oxygen with a double bond is still going to have a 0 formal charge. Okay, so that's another one, and then you can do obviously the same thing with the top one, because you could create the double bond between the top oxygen and the nitrogen, and in that case your resonance structure would look like this, where the top oxygen will have a double bond with the nitrogen, and the side oxygens will have a single bond. And it's in a very similar situation than the other resonance structures, where we got -1 on those 2 oxygens that are single bonded with the nitrogen, and a +1 formal charge with the nitrogen, and the double bonded oxygen is going to have a 0 formal charge. So when you're looking at the distribution between the 3 formal charges, it's actually the same type of atom that's getting the positive charge and that's getting the negative charge. There is no difference in them. Okay, so since there's no difference in who's getting the negative charge and who's getting the positive charge, they are actually going to be an equal contributor of the resonance structures. Okay, so there's a good chance that all 3 of them are going to be, let's say, 33% at a time to make up a total of 100%. Okay, so when I draw the so-called resonance hybrid, the resonance hybrid shows all 3 resonance structures in one structure, and where you can see the double bond kind of rotating. So I'll have each of those oxygens are obviously single bonded, okay, and then you can see all these oxygens can have 3 lone pairs of electrons, but then at the end of the day you have a double bond kind of rotating in those 3 positions. So that's going to be your resonance hybrid structure. Okay, so this is going to be the resonance structures for the nitrate ions. You got 3 resonance structures. There's really not any difference among those 3 resonance structures, so they all have an equal opportunity to be the most stable resonance structure. So sometimes that does happen. Okay, so let me take another example. Let's assume I have this CH3COO1-. So this seems like you have multiple centers there. Both of those carbons going to be the central atom. So if I go ahead and calculate the total number of electrons there, so carbon has 4, I have 3 hydrogens, so each hydrogen brings in 1 electron each, so that's going to be +3. and then there is another carbon that's going to be 4, and then you have another oxygen, that's 6, another oxygen, and then there is a minus charge that gives you a minus plus 1 there, because remember, minus charge means you are electron rich, so you got to add that many number of electrons in there. So this comes out to be 24 altogether. So 24 electrons in there. So since I have two central atoms in there, so I'm going to have carbon and a carbon there. Those are the two central atoms, and they're bonded with one another. The first carbon is surrounded by 3 hydrogen atoms, so I'll draw the 3 hydrogen atoms like these. And then the other carbon is surrounded by the oxygen, so I'll draw those oxygens as far away from one another. Okay, so then I can go ahead and draw one bond between the central and the surrounding atoms, one bond between the two central atoms, the carbon and carbon, and then I can draw one bond between the carbon and the oxygens. Okay, so that uses up how many electrons? So count the number of bonds here. So 1, 2, 3, 4, 5, 6 bonds. So that uses up 12 electrons. So that means you still have 12 more to go. Now, I want to complete the octets of every single surrounding atoms before I move down to the central atom. Now recall, the hydrogens don't need anything but just a single bond, so they are happy as it is. So now you shift your focus onto the oxygens. Now right now, each of the oxygens is having only one bond, which means they have only one electron pair that gives you 2 electrons total. So go ahead and put it in 6 electrons around each of the oxygens. That uses up the remaining 12 electrons. Alright, so before you actually finalize your structure, you got to make sure you actually have everyone happy in terms of the octet. And it seems like this first carbon is fine, okay, so that one is good. And then this second carbon, it doesn't really look that good because it's got only 3 bonds around, so it has an incomplete octet. Okay, so what can be done to make this octet completed? Well, there's 2 possibilities I can do. I can use the lone pair from the top oxygen, okay, and then create a double bond like this. So in doing so, my resonance structure would look like this. All right. So that's one possibility, and then again, the question you want to ask yourself, why the top oxygen is so special getting the double bond, why not the bottom oxygen? And the answer is, well, the bottom oxygen can also make the double bond just like the top oxygen can. So if the bottom oxygen's lone pair is used to create the double bond, then your resonance would look like this. All right, so that everything is going to be fairly similar to the first one except the position of the double bond between the carbons and oxygen. Okay, well, if I go back and figure out what the formal charge is going to be on those, and you might want to take a minute here and calculate the formal charge on every single element there. Hydrogens, once they have one bond, they have a formal charge of 0. Carbons having 4 bonds will have a formal charge of 0. So both of those carbons in both of those structures has 4 bonds. They have a formal charge of 0. Okay, well, when you look at the oxygens, whenever oxygen has 2 bonds, 2 lone pairs, has a formal charge of 0. And remember, if you don't have to necessarily memorize this, but oxygen, carbon, hydrogen, nitrogen, those are the most commonly used atoms. So it's a good idea to know what the formal charge is going to be on those depending on the number of lone pairs and the bond. And it really helps, especially in organic chemistry. Okay, if you don't have it memorized, go ahead and use the formula to calculate this. Okay, so then the carbon oxygen with a single bond, when you calculate this, it's going to have a formal charge of -1. It's a very similar situation what we have in case of nitrate ion. Okay, when you look at the second structure, we have -1 on the top oxygen and 0 on the bottom oxygen. So there's barely any difference between the resonance structures of those two. The only difference you have is the position of the negative charge, and that negative charge is between the oxygen atoms. So that means both of those are actually going to be an equal contributor for the resonance structure. So both of them are equally stable. All right? And then sometimes they ask you to draw the resonance hybrid. So the resonance hybrid shows just the movement of the double bond. All right, so the double bond could be between anywhere on those two oxygens. So that's going to be your resonance hybrid. All right, so hopefully this video was helpful, and I'll have some more videos posted.